Okay, let's move away from linear functions and rate of change in terms of slope. And let's actually take a look at this idea of an instantaneous rate of change of a function at a particular point. So what we want to do here is we want to approximate the instantaneous rate of change. And we'll keep this kind of simple. We'll stay with our quadratic parent function f of x equals x squared at x equals 2. Now then, to kind of recap what we've already talked about with x squared, we know that it doesn't have a constant rate of change. That's only true about linear functions. But we were able to make some statements about this function and its rate of change at various intervals or at various points. And so what we want to know is, what is that rate of change at that exact instant when x is equal to 2? So let's take a quick graph here. And I'm going to kind of just focus in on the first quadrant portion of our parent function. And so I'm going to place the point 2, and that means that we will call this point right there 4. So it's important for us to know that we can actually say what the function value is. F of 2 is equal to 2 squared, which is equal to 4. So what we want to say is, okay, here's our parabola. What is the rate of change at this exact instant? So one of the things we already know right off the bat, because the function is increasing here, that our rate of change is going to be positive. We know that it's going to be larger than it was over here at 1, but it's not going to be quite as big as it is, let's say, at the point 4, 16. And I'm going to go ahead and label that point on my graph as well, the point 4, 16. And it may not be perfectly to scale here, but it's going to accomplish what we can do. Well, I can't really apply the slope formula to something that doesn't have this constant rate of change, but I can approximate using that slope formula. So what we can do, instead of finding the instantaneous rate of change right here at exactly x equals 2, what we can find is something called the average rate of change. And we'll kind of formally define this idea of an average rate of change. But what I'm basically going to do is I'm going to take this point 2, 4 that we already established, and I'm going to say, okay, I'm going to use f of 2 equals 4, and I'm going to use another point on the graph, which is why I labeled I'm going to use another point on the graph of f of x. And since I've already got the point 416 labeled, that'll be the point that I use to go ahead and figure out what the average rate of change is over 2 to 4. And so what we're actually going to do is we're going to take these 2 points right here, and we're going to find the rate of change, or the slope, between these 2 points. And what we're going to be forming is we're going to be forming something called a secant line, and that is a line that connects 2 points of a function. So what I'm going to do here, let me kind of make sure before we actually start doing some computation that I convey exactly what we're trying to accomplish here. I want to know what is the exact rate of change at this point x equals 2. And what I'm going to do is I'm going to go down here to 416, and I'm going to find the average rate of change between those 2 points. I'm going to find, and I tried to kind of make sure that I moved off of the parabola so that you can see what I'm doing here, but I'm going to find the rate of change, or the slope, of this secant line and let it kind of serve as an approximation. And so I'm going to look at this, I'm going to call it a delta x of 2. Because I've moved 2 away from 2 to go down to 4. So for delta x equals 2, I already know that f of 4 is equal to 16. And so if I want to find the rate of change, very similarly to what I did in the previous video, I can say that's going to be f of 4 minus f of 2 over 4 minus 2. Well, f of 4 we already know is 16. F of 2 is 4 over 2, and so that's 12 divided by 2, which is 6. So the rate of change, or the slope of this secant line, is 6. Now then, if you kind of look at it logically, you can see that's an over-approximation for what I'm trying to find, which is the instantaneous rate of change here at 2. This line is steeper than what's actually happening at x equals 2. And so if I want to improve my approximation, it looks pretty intuitive that what I need to do is I need to move a little bit closer to 2. I used a pretty large delta x here going from 2 to 4. Let's bring it in and say, let's make our delta x equal to just simply 1. So rather than using the point 416, I'm going to use the point f of 3 is equal to 9. And then I'm going to apply this same rate of change formula. So I'm going to do f of 3 minus f of 2 over 3 minus 2. So I'm still using the 0.24, but now I'm just bringing this 416 in closer. And I can say, well, f of 3 was 9, minus f of 2, which is 4, all over 3 minus 2, which is 1, and that ends up being 5 over 1, or 5. So I've made my rate of change a little bit less steep here, and I'm getting actually a lot closer to what the rate of change is at x equals 2. Well, if I want to get even better, I can take delta x, or I was using the 0.39, and I can say, okay, let's move it even closer and say delta x is going to equal 0.1. And so in other words, I'm going to use the 0.24, and I'm also going to use the function value at 2.1. And if you square 2.1, the number that you get is 4.41. And so now I can use my rate of change formula and say, okay, I want f of 2.1 minus f of 2 over 2.1 minus 2. And that comes out to be, when I substitute these in, 4.41 minus 4 over 0.1. And if you do the computation here, you get 0.41 divided by 0.1, and what that value comes out to be is 4.1. So again, I got a little bit closer to what the actual value is. Well, let's go one more. Let's use a delta x equal to 0.01, and I could continue this exercise on and on and on, just keep getting closer and closer and closer to 2. So now I'm using the point at 2.01, and if you square 2.01, you get 4.0401. So my rate of change formula is f of 2.01 minus f of 2 over 2.01 minus 2. And if I substitute these in, I get 4.0401 minus 4 over 0.01. And you'll notice my change in x always ends up being the denominator there, and that comes from our change in y over change in x formula. Well, if I look here, 0.0401 divided by 1/100 ends up equaling 4.01. And there's kind of a trend that's emerging. I go from 6 to 5 to 4.1 to 4.01. It sure seems like as this change in x is getting smaller and smaller and smaller, and as I'm getting closer and closer to 2, it sure seems like my rate of change is getting closer to 4. And in fact, it is. So I'm going to go ahead and say, as delta x is approaching 0, which is what we were doing here. We were going from 2 to 1 to 0.1 to 0.01. We were making it smaller and smaller and smaller. So I wanted delta x to approach 0. And if you think about this idea of an instant, that's really what we're talking about. We're talking about when no time passes. So as this delta x is approaching 0, the rate of change of f of x at the point x equals 2, it sure looks like this rate of change, which we were calculating as we went along here, that it itself was approaching the value 4. And you don't know it yet, but there's a lot of power in this statement that we just made. That as the change in x was getting smaller and smaller and smaller and approaching 0, the rate of change of the function was approaching a specific value 4. As we start to really define limits and this idea of rate of change in the derivative, there's a lot of power packed into this statement right here that we'll be exploring in the next couple of units.